If you start from the Helmholtz equation and you impose that this equation is orthogonal to any arbitrary function, can you then also show that this is equivalent to minimizing this particular variational form over here? So pause the video to think about this, and small hint, I would really try to prioritize thinking over doing very long and elaborate calculations. Let's have a look at what we did in the notes in the textbook. So in the textbook, we actually started from this variational expression over here. And then we did lots of calculations to finally arrive at the conclusion that this was equivalent to saying that our function psi satisfies the Helmholtz equation over here. Now you might notice that the last but one step over here is a bit peculiar, because it basically tells us that if we take the Helmholtz equation and we multiply it by an arbitrary function, which here we called delta psi, and we interpreted that as the first variation, but it's basically just an arbitrary function. And then the resulting product, we integrate that out over the entire volume, that basically gives us a zero. Now this is equivalent to saying that our equation here is orthogonal to an arbitrary function under a scalar product, which consists of the product of these two functions integrated out over volume. So the question we need to solve here is basically, if you start from this particular position, can you work your way back to the beginning of the proof? Let's see if we can do this. So let's scroll back up. The first important thing we do is this particular term, which appears here. So this is a term related to the boundary conditions, but we argued that this term is zero. So we just introduce an extra zero here on the right-hand side. And then the next thing we do is we bring this term to the left-hand side, then rearrange stuff a little bit. And the zero, we're going to write that as delta j, so, but that's just notation. So then we have this rather complicated expression, but then we use our incarnation of Green's theorem, which was mentioned here, to end up with something like this, where delta j is given by that expression over here. So now what we need to do is just add the terms that we neglected when we went from this step to that step. So these are all the terms involving higher order variations. We just add those back in, and then we can write it as follows here. Now this step is a little bit hand waving, because this equal sign over here is actually an approximately equal sign. So we pretend that we can safely go from an approximately equal sign to a bona fide equal sign, but let's just sweep that under the rug here and assume that we can do that. And then finally, we can write down an expression like this, which we can clearly identify as being the first variation of this particular variation expression over here. So this is how we can show that this is more or less equivalent to demanding that the Helmholtz equation is orthogonal to any arbitrary function.